So we have heard from my colleagues about one problem, one application of machine learning technologies to medical imaging, which is detection of different diseases on radiographs. And while this is a great example, a great data set, and a great way to learn a few things about applying machine learning to these sorts of problems, there are actually a few issues with this data set and with this problem. So if you look it up online, this data set comes data set comes from NIH, and there had been a Stanford paper published around that. So there is some criticism of radiologists of the data set itself, of the way the labels were applied, and of the clinical utility of the problem. So you can see very good results, but if you were trying to deploy it in the clinic, actually the utility might not be as questionable. And it is a very not straightforward and very kind of unclear process of identifying such problems where there is a lot of utility of the algorithm that's solving this problem. So this is one problem that we looked at in this project, and I'm going to talk about it in the next half hour. So first, the motivation for this. The problem selection has to do mostly with different kinds of cancers, and as some of you might know, cancer is the biggest killer among the chronic diseases. And one thing to note here is about half of cancer patients are treated with a method called radiation therapy. And radiation therapy is a procedure where a patient is put on a table like that under a huge kind of machine that can move around and can deliver a very targeted beam of ionizing radiations or particles to blast the tumor, the organ that contains the tumor, with a very high precision. And it can be targeted in a way that it spares the surrounding organs, minimizing the damage, to what's close, which allows treatment of very fine things like tumors in the brain, for example, glioblastomas that are located close to some other vital parts of the brain. Surprisingly enough, the the use of this complicated machine, it's all guided by a human who will at some point sit down and look at what's called a CAT scan. It's a form of medical scan similar to X-ray, with the only difference being that it's a three-dimensional data set, right? So it's many slices through a human body. So, and someone will look through the set of slices and will do something similar to what we see to the right here. They will trace the organs, not only the organs that have the tumor, but also the organs that are healthy but just need to be tracked or spared or need to be minded when the treatment is planned. And as you can imagine, when you have like 100 slices, for example, that contain these organs, it's a very tedious process. And it's in this case, we're looking at someone tracing a bladder for a patient who has probably prostate cancer, and it would take them anywhere between 40 minutes and an hour to delineate all the anatomy there. And the question is, can we develop a segmentation algorithm that will do it automatically and save someone an hour of their time? Another problem, which comes from different area of medicine, but is actually quite similar, is in radiology. So in radiology, there is this workflow where someone analyzes the set of what they call longitudinal exams. Right. So in this case, someone has a brain tumor, unfortunately, and they are being seen at the hospital probably every 3 months or every couple of months, and they undergo different types of treatment, radiation and chemo and surgery. And a radiologist, a person like Mazen here, would be asked to take a look at an image and report on this image, right? So tell what's happening with the tumor. The problem is that with current set of tools, there are very little that they can do in terms of quantifying the change of the disease. It's not even common for someone to take a look at the prior exam, not to say about 10 prior exams, and compare them. So literally what happens is that a radiological report would look somewhat like that. We're circled in red here, for those of you who can't quite see. The radiologist wrote that there is an increase in size of the left frontal blood-brain barrier. Right, so as a computer scientist, you might be prompted to ask, like, okay, so how much of an increase, right? Is it significant? Is it not significant? Well, we don't have, there aren't really good tools in medicine to quantify the increase in size. And when there are tools, something like this happens, right? So there are standards for actually measuring the tumors, but these standards that the radiologists use right now, they look somewhat like that. So they would be asked to find the slice of the many slices. Remember, we're dealing with three-dimensional images that has the largest area of the tumor, and they would draw a linear, simple linear measure, or maybe two linear measures, right? And say that the size of the tumor is 80 millimeters, or 80 millimeters by 20 millimeters, right? So you might be prompted to ask, like, why not measure the volume, right? The volume would be much better predictor of how large the tumor is. And actually, in this example, we're seeing that this linear measure is not really predictive of what the volume is, right? So we're seeing the linear measure increase by 14% and then decrease. Oh, my minus sign is missing there, but it's actually decreased by 25%, right? But the volume has increased by 18%, right? So it's actually pointing in the other directions. And unfortunately, that happens all the time. And the question is, can we develop a system that will automatically measure the volume and will provide these quantitative measures? And the important thing to mention here is that radiology is quite different from radiation oncology, right? So the radiologist does not have an hour of their time to spend delineating this tumor, right? They're asked to provide the reading very quickly. So that's why this sort of accurate tracing does not really happen in radiology today. And then there is another problem in surgery. So a lot of surgical procedures right now are done with an endoscope, and this is where a surgeon is basically poking a patient with a camera and then trying to understand what to cut and why to cut, why and where to cut by looking at an image like this one to the right. So sorry, this is a bit kind of gory, but they're tracing out the tumor here. And the challenge is that they have no way of knowing kind of how this relates to arteries, how far the tumor goes. And oftentimes they either place a laptop with images next to their endoscope view, or they have to get up and walk back to a machine that has images open to understand kind of the anatomy. And a lot of surgeons would love to visualize the 3D anatomy on top of this video, and they would love to have the delineated arteries and tumors and all the anatomy in 3D in front of them when they're doing the procedure. And again, sounds like a good case for segmenting, for an algorithm that could segment the anatomy quickly and visualize it. So that's what the project is about, right? So we've seen that the problem of image segmentation, of semantic image segmentation, pops up in medicine all the time in various places, and that's what we're trying to solve with this project INRAI. So here, for example, you're seeing some of the results that we were able to obtain with our brain tumor segmentation model. This research goes back to Kinect. So Kinect, some of you might know this product, which is a camera and add-on to Xbox, and Kinect was able to Kinect actually sees a RGBD image, right? So it sees the flat picture, but also it can sense the depth. So you have kind of four-dimensional image there. And in Kinect, they developed a machine learning algorithm that was able to classify every pixel. It was very efficient. It was based on a random decision forest, and it was running at 25 frames per second on like 10% of Kinect's CPU. And it was able to produce something like that, right? So segmentation, remember kind of the what we talked about in the beginning, is about labeling every single pixel or voxel in this case, since we're dealing with 3D image, with some label that holds semantic value. In this case, the semantic value is whether it's left arm or right arm or head or chest or something else. So actually, at some point, we thought that this problem that was solved for Kinect is not that much different from problem in medical images. You're dealing with 3D data, and you're trying to identify what's happening in this 3D image. And that's where the project started about probably 7 or 8 years ago. So to present the problem more specifically, what we're doing for three-dimensional segmentation, we have image like the one on the left here, and we're trying to obtain the image like the one on the right, where all the relevant anatomy is labeled, and each label has some semantic meaning. Like in this case, and this is what I will use in my examples, we're looking at again, scan of a male pelvis of someone who has prostate cancer. We started with this case with prostate cancer because actually prostate cancer has a very high incidence, and it was relatively easy for us to obtain good ground truth data because many radiation oncology centers already have this data because they do the tracing in their course of treatment. But the challenge of segmenting this type of anatomy, right? So think about it. It's first, it's three-dimensional, so we have one extra dimension compared to X-rays that we've been dealing with so far. And also with the segmentation, you need to predict something about each voxel, right? But it's hard to just go off the intensity of the voxel because you have first these two organs here, right? So we're looking at the prostate and the rectum here, and they have similar, same intensities. And in this slice, we have some artifacts which might be present in some patients, might be absent in others, right? And then there are artifacts coming from different scanners and all kinds of things like that. So this sounds like a perfect problem for machine learning. We did just that. We applied the algorithm, which I talked about before. The ground truth for the algorithm, the training data looked like this. So we took the data from radiation oncology. We worked with clinicians to help us curate this data set and get it to a consistent shape, which was quite an ordeal because we learned that different centers actually like to label to trace their contours in a very different ways. That's what the ground truth is. And we use the machine learning algorithm, which is based on what we've done for Kinect, but it's kind of a little bit different. I won't go into much detail here in the interest of time, but it's based on random decision forests. And we use one additional concept, which it's not really our invention, but I think we are the first group that applied it to the problem of medical imaging. So we're using multiple layers of this forest, and each layer produces some sort of prediction, which is used as an input into the next layer of forest. And since the features that we use to, predict to obtain the information about each particular voxel, they kind of sample from some sort of receptive field, right? So some area around this voxel, right? So we can sample also from multiple channels. So that way we have at each layer, we have input from the original training set, plus we have input in the form of probability and in form of predictions, similar to those activation maps that we've seen earlier. We have another channel, right? And that's why we can sample from multiple channels. This is not what you would typically expect from computer vision machine learning algorithms. So we're not using deep neural nets, and we've actively considered using neural nets for this. So far, we've seen that decision forests, they have some advantages. First and foremost, they are much faster at runtime and train time. They don't need as much data because they don't have as many free parameters. And it's kind of easier to deal with them, and it's easier to produce natively 3D features. At this point, you have the problem, you have the data set, right? So this is kind of where the rubber hits the road. You need to actually prove to the clinicians that it's useful, right? And prove to them that it makes sense to deploy it in clinical practice. Yes, there is a question? You know what? Why don't we? I'll get through the talk because I have some content here, so I really don't want you to hold everyone here longer than needed. And then I have a few slides, kind of going into more details. We can stay a bit longer, and I'll go through those. I just don't want to derail the conversation. Yeah, it's a stack of random decision forests. I'll return to that after the body of the talk.
Slice of that and prediction at every XY layer, and then
Uh, Right, let me quickly show show some slides since there is some interest. We're doing something different. So in the training, we analyze every voxel in the training set, and we put together this kind of receptive field, right? So we look the optimization that happens at every node of the tree that's being trained. We optimize those features, right? So features which are these probe voxels. So we have some area around every voxel which we sample. Right, and then the optimization criteria would be to come up with such a configuration which will achieve the best split on the training set, right? So such a training configuration that for this particular voxel in this area would result in, for example, images that voxels that belong to the say bladder go to the left branch of the tree, right, and all the other voxels go to the right branch of the tree, something like that, right, and then. These are the features that we use, right? And then kind of the standard decision tree pattern happens. So the features, they can be presented as some sort of hyperspace, which we partition during the training. And then during the testing, we basically, the algorithm runs and it identifies every voxel as belonging to some of the partition of the space. And that's how we achieve the classification. And this is kind of, yeah. The features are like in this case, the features would be locations and intensities of those voxels. Yeah, X, Y, Z, and like in medical images, you have intensity, right? So it's grayscale, and it's actually it can be up to 32 bits of grayscale. Yeah, we compress it down to 16. Yeah. Yeah, and we call them deep decision forests because after we train one tree in this manner, right? So first, what is a random forest, right? You train multiple trees, and because each individual tree might have a tendency to overfit, when you have multiple trees, when you average the result, you kind of control your overfitting this way, and then there is this kind of secret sauce that we have of stacking those forest layers. Right, so each forest layer produces an output, and then we train another layer. But the sampling happens not only from one image, right? The sampling happens from the image in the training set, and also the prediction from the previous layer of models forests. So this is. And apologies for kind of rushed explanation, but we have some great content on our website. If you're curious, I'll post a link to that. You're welcome to take a look at more detailed lectures. And we actually have a book on this stuff. So one of our researchers wrote a book on medical image analysis using random decision forests. But at this point, right, the question is how well does it perform in the field, and does it make sense for a clinician to use this in their practice? We've done this test with our what we call prostate model, the model that's used for prostate cancer patients in radiation therapy procedure preparation. We've asked for 3 different radiation oncologists to segment the anatomy on 10 different cases, 10 different patients. And then we've compared that, well, actually the average of that, with how well the model performed on those cases, right? The ground truths that we've considered were the actual contours used for treatment. And we've seen this picture where we have the mean, we have the median and the standard deviation. It's actually half a standard deviation. So we've seen that kind of strictly speaking, statistically speaking, right, the machine learning model that we've developed is not much different from another human performing the same task. Right, and we're seeing that, for example, in case of prostate, which is a kind of squishy organ, which is different in each image, it's grayscale, kind of hard to spot. There is, so these numbers, right, I should have mentioned probably, they reflect how well the humans agree with each other, right? So it's a measure of similarity between all the segmentations. And they are not perfect because it is not clear, right? So some people would not agree precisely which voxels belong to certain organs. Yep, had a question.
So one thing I'm worried about is that they are very highly fit to the exact location, the exact XYZ location to where each like where the bladder occurs or something.
Mm-hmm.
That must mean that you have a fairly
It's actually, yeah, you would think so, but it's actually turns out that in practice it could be less stringent than you would think. We do resampling, so all the images are resampled. Huh? Yeah, resampled. They are resampled. So as you might imagine, right, we're talking about 3D sets. So these are sets of flat images. So each image can be like 512 by 512 pixels, right? And we can have 100 of those with, say, 0.3 millimeter step, right? In the training set, we can have a variation. There could be 0.3 millimeter step, there could be 1 millimeter step, that could be 3 millimeter step, right? All the images are resampled to 1 millimeter steps, right? So we have this 1 by 1 by 1 cubes which represent each voxel. So this is what we do. This is probably the most stringent kind of conformance operation that we do. But other than that, right, this is where the power of random forests come in. If we were to use just one tree, yes, it would have overfit terribly. But when we use multiple trees and we average the results and we use some randomization in how the trees are trained, and randomization comes up in this sampling of the voxels, that's where things start to generalize pretty well. So really, sorry, I don't want to derail the conversation, right? It's getting longer than the time I have. Like we have like 10 minutes left. We can chat after the talk. I'd be happy to go into detail. Yep.
Pretty quick one. So what are the hyperparameters you choose for these?
Mm-hmm. Yeah, the hyperparameters would be how many trees do you use on each layer, right? How many layers of trees do you use? What sort of feature types do you use? So that sort of stuff. And we've seen kind of experimentally what works best.
The trees have different parameters. Do you use like same throughout?
Frankly, we use same throughout. Yeah, so see, each layer looks exactly like the previous one. You could go further and kind of optimize it down to layer level. We've seen good enough performance with what we've seen. And for example, this model, the prostate model that shows this sort of performance, it uses I think like 10 layers of 15 trees in each layer. So it's not something humongous. And so we have that, right, where we can see that the model performs actually similar to humans. And we've done another test, right, which we compared the performance of the machine learning model with other auto-segmentation algorithms. Since we're applying that to the problem of radiation oncology, there are tools already on the market that do that sort of thing, where clinicians do their auto-delineation. These tools have actually auto-contouring features, auto-contouring packages, which the manufacturers of these tools often sell as a separate add-on for quite a hefty sum of money. And we've seen that and none of these packages work actually using machine learning, right? So they work using what's called an ABAS, which is a atlas-based segmentation. So it's a different sort of technology based on heuristic image features. So basically, they're trying to find a best image which looks most closely to the image that you are currently examining, and they're trying to morph it to fit your current image. And we've seen that these algorithms work kind of okay when you're looking at non-deformable structures like bones, because on CT scans they show up like as bright white voxels, but they fail often when you're dealing with structures which change from patient to patient and within a patient, like this prostate and rectum, for example, which are soft tissues. And we've seen some interesting failures, like in some cases the algorithm would place a femur, a bone in the right place, but the bone would be upside down, right? So it would be pretty much useless to the person trying to contour this sort of anatomy. And this is the kind of error that machine learning would not make. So at this point, I will show you very quickly a tool that we have developed. So we actually went ahead and we built a tool for contouring. So this is a tool where radiologists could radiation oncologists could come in and do the segmentation, similar to what I've shown in the little video clip in the beginning. And also in this tool, they can call the machine learning algorithm. So in this case, we're looking at a CT scan, right? So you might see kind of familiar images similar to what we've seen in the beginning, grayscale images. But now I'm going through the slices right from top to bottom, and you can see how the slices change, right? So I'm kind of going through different parts of the anatomy. In this case, again, we're looking at a CT scan of a male pelvis, a patient who has a prostate cancer. And in here, I can go ahead and do something similar to what a radiation oncologist would do, just segment the bladder. Right now, I would go on one slice, I would draw a boundary around the bladder, and it would produce a segmentation. I would switch to another slice, I would do the same. So, you can appreciate that it's quite painful. These guys are actually super quick with this. They use this Wacom tablets and all that, but still, it takes time. Right, but also I can click this auto structure set button. So here we have a few machine learning models that have been trained. As you can imagine, each type of anatomy, each type of image requires a new machine learning model. What we've been able to achieve is that the algorithm stays the same, right? You just need to fit it a different type of image, and we'll actually tune a few hyperparameters. But once you've done that, that's kind of not as much of a work as developing a whole new algorithm. So, the algorithm is off to analyze this image. In this case, I'm running it locally on my machine. And in this case, we're dealing with a data set that has 98 512 by 512 images, right? So we're running it over every single voxel. And it's already done, right? And you can kind of appreciate the accuracy even without being the clinical expert by looking at this region where we have the overlap of several important structures, right? We have the bladder, the prostate, the rectum, and it's really hard to tell where is what. So the machine learning is able to discriminate between those voxels with a pretty good degree of accuracy. And in this tool, right, we have some, when we're thinking about deploying that to the field, right, of course, the clinicians would want to have the ability to correct the segmentation, and but once they've corrected it, they could send it on to the treatment machine, and and hopefully it will have saved them a lot of time. And also we have this neat kind of 3D visualization in this tool, and some very quick examples. Like for example, here we have another case which is quite different. We're looking at an abdomen now, right? So the kind of the chest. And again, it's a 3D image. Right now, we're looking at a reconstruction, right? So it's called volumetric reconstruction. So basically, all the voxels are plotted in the 3D space. And in here, you can see this brighter, branchy structure in the middle. This is the aorta, the main blood vessel in the body. And currently, it has the contrast in this image. So it has the something to light it up on a CT scan. And I won't run the segmentation live. In the interest of time, I will just turn on the pre-segmented image. And you can see that the problem is quite different here, right? So this aorta, it has a lot of thin and connected structures, but still the same model was able to figure out where it is and classify it and figure out how it connects to kidneys. And also we have other parts of anatomy here, like we have kidneys, for example, which look pretty nice. And we have a vein, which is a bit tougher than aorta in this case, because if I switch to this, what's called an axial view, right, you could see that actually aorta is bright white, right, because it's high contrast, it has a contrast, but vein is actually this mushy gray, and it's, again, would not be that easy to discriminate between vein and other structures. So that's kind of the tool that we have and the tool that we use with clinicians to evaluate the utility of the model. So, and at this point, coming back to the presentation, right, having this technology, what you can do with it, and what I was thinking about, right, radiation oncology, right, you have this long and tedious manual process. So, you can replace this process with automatic segmentation and actually give clinicians back their time by reducing the segmentation times from hours to minutes. In radiology, so remember the tracking of the tumor size over time, right? We can easily auto-segment every image that comes into the clinical image storage system and produce a segmentation, produce an accurate volumetric measurements, maybe have a radiologist check it and, and correct it if it's not right. But now we're given a very powerful tool to radiologists, a tool that allows them to measure in a very consistent way the change of the tumors. And in this case, you could see that, for example, if you're able to measure the tumor and the actual inflammation that sits around the tumor, or enhancing tissue as they call it, you could see that at some point maybe the tumor is reducing in size, but the inflammation is actually going up, and it's consistent, which might make a think that it is something is happening. Maybe the tumor is recurring. And we've talked about surgery, right? So in surgery, a lot of people are thinking about doing this AR-assisted surgery, right? So there are a lot of ways of improving both surgical planning and surgical navigation, but all of those use cases are rooted in the accurate segmentation of tissue, and this is another area that we're working at. So last kind of slide to remember here, we're thinking of deploying that as an services on top of Azure, and maybe it will be something that you could use and call and use in your own applications and build something even better and cooler on that, because once you have a segmentation of an organ, there are a lot of different cool things that you can do with machine learning to analyze further what's happening inside the organ, discriminate between healthy and diseased organs, and many other things. This is actually in private preview, so we're inviting companies who are active in the space to collaborate with us. So with that, I conclude. Sorry, I think I'm a bit over time, but hopefully this was interesting and informative. Thanks a lot. We have a question. I'm sorry? The tool? No, sorry. We provide this tool to our collaborators with whom we work to evaluate the models, but yeah, at this point we don't let people just download and play with it. But if you work for a hospital, we'd be happy to talk to you about giving you this tool. Yep.
So what kind of images so far? How about ultrasound? Is that something?
We are dealing, so the 3D images, which are consistent and are a good fit for this sort of problem, are CT images, computed tomography, and MR images, magnetic resonance imaging. There is ultrasound is kind of getting there, so there are 3D ultrasound images. We haven't really looked at them because it's harder to get ground truth, and they're not very consistent because of the this shape distortion that happens. Yeah. All right, well, thanks a lot. I will be here if you have any questions.